Okay, so we have the Green's theorem, which says if you go around the region counterclockwise and if you compute f dot dr, if you do this line integral, it's equal to taking a double integral over the entire region of the curl. This is a two-dimensional version of the curl dA. And we actually proved this by taking this and dividing by the area and shrinking the domain into a very, very small region. We used the square to calculate it, but you can try other regions too. You can try rectangle and shrink it down to 0. You can also try with circles. I never tried one with triangles myself, but you can very well try a triangle and compute that and see what that gives us. It will always give you the same thing. Regardless of the shape that you start with, when you divide the curl by the area and shrink the domain down to 0, you always get the curl. So curl should be thought as like a point-wise circulation. So at that point, if the curl is positive, it means that at that point the vector is rotating counterclockwise somewhat. And if the curl is negative, that means at that point the vector is rotating clockwise. If it's 0, that means it doesn't rotate at all. That's the geometrical meaning of the curl. All right? But I guess for us, the question will be, okay, so fine, we have such a good theorem. What is it good for, right? So I have to also justify why we would like to use this theorem at all, right? It seems like a nice theorem, but if it doesn't have any applications at all, then why would we want to use it, right? So here's how it goes. Let me show you this example. Let F be a vector field, which is like 5x minus 2y, 3x plus 7y, something like this. And then let's say let C be a semicircle shaped path on the top half circle of x squared plus y squared equals to 4. It's like a radius 2 circle. From negative 2, 0 to 2, 0. Compute integral of C f dot dr. Okay, so let me draw a picture so that you understand what the question is. So this is a circle of radius 2. Here's negative 2, 0, and here's positive 2, 0. And we're talking about the top half circle, not the bottom one. And what's the C? C begins from here and ends there, so it's this curve. Over this curve C, we want to calculate f dot dr. That's the question. Which is definitely something that you can do, right? I mean, you can parameterize this circle by what? You can do 2 cosine t, 2 sine t, right? That's how you parameterize a circle, right? And this is when t is pi, and this is when t is 0, so you can say, oh, t should go from pi to 0, with this being your RT. And then what it means is that you have to plug in these into each of the x and y. You have to differentiate the dot product, and you integrate from pi to 0. And you do this calculation. At some point, you will need the calculation to include something like sine squared of t equals to 1 minus cosine 2t over 2. This formula will be needed if you do it that way. And you should also use cosine squared t equals to 1 plus cosine 2t. That will be needed. So this is definitely a question which you can do without any help of the Green's theorem. Okay? But it takes a while. I mean, in fact, I might actually give you this question and say I'll do it in 2 different ways and show that they are the same. One using the Green's theorem, one without using the Green's theorem. Okay? So you should definitely try to do it this way and see that it works. But I want to show you how you can make use of this one. Right? So are you kind of convinced that doing it this way will be quite a calculation?
Yes.
Yeah, it's going to take like at least 10 minutes, I think. Yeah. All right. So how do you make use of this? Well, notice that the Green's theorem requires a domain. Here I only have a curve. So I have to pick a domain that includes this curve as part of its boundary. What should I pick as the domain? Domain. Domain is a region in the plane.
Oh.
What shape?
Oh, circle.
Okay, we can choose the entire circle, but that's not the desirable thing because you'll see why. It's not the one. Yeah.
Would you do 0 to 2? Like, could you?
No. I want a domain. I don't want an interval. I want a domain. What's a domain? It's some region in the 2-dimensional plane. Okay. I'm saying the circle is not good because the other side is also curved.
You want the positive square root.
Yeah. So I want this half disk. Okay. That's what I want. Yeah.
Would that be like
What?
0 to 2 to pi, 0 to pi?
I want this disk. That's it.
Well,
What else do I have to say?
X0.
Oh, to evaluate this, you want the equation. Is that what you want?
How is
Oh, okay, yeah. I mean, you could do that. I mean, if you do like x as -2 to 2 and y as 0 to square root of 4 minus x squared of this curl dy dx. Certainly, that's one way to do the right side. But we're gonna do it easier than that.
Are you
Okay?
talking about like half of the area of the circle?
Yeah, that's
no,
what's
1/2
gonna.
pi r squared.
We are gonna use that, but wait, you're going too fast. Okay, so. All right, so definitely we're going to do that, okay? All right, so I'm going to choose our D to be this. And get rid of these annoying things, okay? I'm not even going to talk about them, okay? So it would be very easy. Delete that, okay? All right, now, how is the domain, how is the boundary of the domain what is the domain of the, no, what is the boundary of this domain made of? A line, right? Let's call this C1. And then? This curve, right? C2. But notice that C2 is really negative of C. Right? It's the opposite direction. So when you do the integral, you're not going to get the same thing as C. They're going to be different. Okay. But anyways, let's deal with that problem later. But we're going to come back to that. But here's what the left side says. The left side says if I integrate over C1 plus C2 of f dot dr, the right side will give me over this half domain, half disk. Let's see, well, what is this thing? I have to put round x, round y. What did I put here?
Oh, you're going to put 5x 2y.
What about here?
3x plus 1, 7.
That's LM, right? That's how you do the curl, 2-dimensional curl, and dA. Now let's try to think about what this means. First, this means you have to do it in two integrals. So one, you integrate over C1. And you have to integrate over C2. Okay, what about this one? How do you calculate this? AD minus BC, right? Partial with respect to x is applied to this one. What do you get? 3. Partial with respect to y is applied to this one. What do you get? Negative 2, but you have to subtract it. It's AD minus BC, right? Okay? Wait, this is just 5, which can be pulled outside, and I end up with 1 dA. Oh, and by the way, on the left side, see, I said C2 is really the opposite direction of C. So if I change this into C, I should put a minus. Okay? So this is what we have. So far, so good? All right. What's the area of this? Oh, I said it, but what is this thing? It's the area, right? If you integrate 1 over the region, you get the area of the domain. I was going to ask you that. All right, good. What's the area of this thing, by the way? 1/2 of the pi r squared. Pi r squared is the area of the entire circle, but we have half of this, right? So you get 5 times 1/2 of pi times, what's the radius? 2. 2 squared is 4. 4 divided by 2 is 2. 2 times 5 is 10, so we get 10 pi. Awesome. Now, what are we going after? Sometimes if you do a lot of calculation, you forget what you're trying to go after. What are we going after here? No. No.
Circulation.
Yeah, circulation.
What was the question asking us about? This was the question, wasn't it? We were doing all the other ones to figure this out, okay? Yeah, don't be, it's just totally confused. All right, so, okay, so we did all this calculation and we got the following thing. Integration over C1 f dot dr minus integration over Cf dot dr is 10 pi. That was our result. But what are we going after again? We're looking for this, right? So what do we need to know?
C.
We're trying to figure this out. I want to make use of this. What should we calculate?
C1.
C1. If I calculate this, I can solve this and I get this, right?
The second one is C2, right?
No, this is C. C2 is negative C.
Oh,
Yeah, it's the opposite direction.
alright.
Okay, yeah. So it's C2, but now it's negative C. Okay, so that means we have to do this. Now, how do you parameterize C1? C1 is this one, right? Let's see. You go from negative 2 comma 0 to 2 comma 0. So what's always constant as you move? Y coordinate is always 0, right? Okay. And x coordinate changes from here to there. Right? So what's that? You can parameterize this C1 as RT equal to y is always 0 and x coordinate is changing, so you just put a t. Where should t vary from? Negative 2 to 2. Perfect, right? That was easy. That's an easy parameterization, isn't it? Agreed? All right. Okay. Now look. I need to calculate this. So let's do this small calculation. Integral of C1 f dot dr. That we really have to do honestly, but it's 10 times easier than doing it over that curve. It's a straight line. How easier can it be? So what do you do? Divide by dt, multiply by dt. The most important trick you shouldn't forget. Okay, and then that means t goes from where to where? Negative 2 to 2. Where do you evaluate your function? The vector field. Yeah, this is your vector field, but it's on this curve. So you put your x is t and y is 0. So t goes into x, 0 goes into y, so I get 5t from here. What about this one? T goes into x, 0 is into y, so you get 5t, 3t. Dotted with what? Dotted with,
1, 0.
yes. Okay,
Way to go, Xander. Redeemed.
where am I getting the 1, 0 from?
Hard.
Differentiate this. It says differentiate, right?
Oh.
So 1, 0, okay? So you get integral from -2 to 2, 5t dt, whose integral is 5 over 2t squared, 2 and -2. Plug in 2, you get 10. Plug in -2, you get 10. You get 0. Super easy. So you get 0 for this, and therefore, what's the answer? Simple.